Ladies and gentlemen, welcome to the KEMET webinar with the following topic, calculating the best power inductor solution. My name is Ivana Ivanovska and I will moderate the webinar today. We are very pleased that you find the time to join our webinar. Joining me on the call today, we have Alexander Nebel, who is our field application engineer for the Central Europe region. Our topic today is calculating the best power inductor solution, and we have on the call Alex. Good afternoon, Alex. How are you?
Thank you. Welcome everybody to our webinar today. For those of you who might have heard about our MPX series on Monday, we will go today a little more deeper and also talk about the applications with this product. So can I start?
Yes, you can start.
Okay. So again, just to give you a short summary, I'm the field application engineer in EMEA, and I'm doing this presentation now also since 2 years. And today I want to go a little bit more deeper and look on components from the application side. So first, only a few slides about basics. What is an inductor? I want to show you what is important with an inductor and why are there so many different types and differences in the inductor world. The next topic is a few slides about DC-DC converter and where exactly do I need power inductors and what needs to be considered when designing in. The third topic, and this is the most interesting topic for today, is the real calculating the inductor values and how I can find the best component. And I will also do a comparison to competitor items. And finally, I give you a short overview about our KEMET power inductor series and which different power inductors we offer at KEMET. So let's start directly. So first of all, to look at the basics. And the question always is, what is an inductor? And very simple answer, an inductor is a wire around a core, any core. This could be wood, plastic, or glass. But obviously, when you put this into a reflow oven, it's not so good to use plastic or wood. So in fact, we use some core material which can resist higher temperature. But we can also choose an air core. So nothing as core material. And then we are talking about an air core. So the simplest inductor we can create is a piece of wire, because a piece of wire has one turn around an air core. To calculate now the inductance, we need to look at different values. First of all, we will have the number of turns, which is n. The more number of turns we have, the higher the inductance is. But we need also to consider if we have 100 turns on an inductor, the component might get very big. The next thing is the effective area, A. So the higher it is, the higher my inductance gets. Also here is, to get a high inductance, I need to increase the size of the component, which is always not wanted. And the effective length I will show you on the next slide. So here we are. This is the black circle here. This is my effective length of the inductor. And for sure, I can decrease the effective length to increase the inductance, but then I have problems in getting my number of turns. So everything I do will always change the size of the component. But as we want to decrease the size of my component on the board to save space and also to have easier possibilities to place other components nearby, it's the best to have a small component. So the best thing to change is the μr, my magnetic permeability. Well, now, I could think about increasing the magnetic permeability to some high values, but there's some behavior. And here we can see directly the behavior of the μr. The orange curve is the μr of a material with 10,000 μr. But the more we increase the μr, the more we change the frequency range to a lower frequency. And this might be a disadvantage, because depending on which frequency I'm using, I want to have maybe a higher switching frequency. And this is a problem. So I need to find the best way of the μr and of the component size. And there might be some limitations in choosing a material, because the higher μr I have, the lower frequency range I have. So I can increase the inductance with high permeability, with a bigger cross-section, with a higher number of turn, and with less effective length of the core. This is the way we as manufacturer can do this. The good thing is you don't have to look at this point. So trust in us, we have done this already. And therefore, we can now go into the DC-DC converter, one very interesting application for our power inductors. So mainly we are talking about the switching frequency. And we have just talked about the frequency before. The frequency is dependent on the material we are using. So the typical switching frequency is somewhere between 30 kilohertz and 1 megahertz. Let's say the most common switching frequency are from 300 kilohertz to 1 megahertz. For sure, I know when you may be looking into the smartphone industry, there might be also higher switching frequency. But this is the standard range I want to look today. But also, when switching frequency increases, we can reduce also the size of the inductor. So downsizing is also combined with the frequency increase. And finally, the current from the switching regulator has AC components, and this will flow through the output capacitor. And depending on the ESR, we will generate a ripple voltage, and ripple voltage is always something we might not want to have. How does this work? So let's have a simple picture on a buck converter. Buck converter or step-down converter is when I have a higher input voltage and want to have a lower output voltage. So, and the simplest way to describe a buck converter is to have a switch, which could be a transistor or an IC, and we have a diode. This is my inductor and this is my capacitor. And then with my switching frequency, I define the on and off phase. So on, off, on, off. This is very simple. Now, what happens during the on phase? During the on phase, my current flow is the green flow here. This is how the current flows. The diode is closed, so there's no current flow through the diode. And then here we can see the current through the transistor, or the switch in this case. On the next slide, we see the current flow in the off phase. Now, as the switch is open, there's no possibility that the current flows from the input, and only the current can flow out of the capacitor through the diode and through the inductor. And now let's see all phases together. And here we see the combination of the last two pages, the green and the red curve. This is my on phase, this is my off phase, and the inductor current is not constant. And this is what we call ripple current. Well, the best thing is to have no ripple current, but we have a ripple current. And with the capacitor, with the output capacitor, and most of you might know that we have the best solutions from KEMET to choose the right output capacitor, we can smooth this curve here a little bit. And now let's go into detail. And this is the main part of today's presentation, how to calculate the inductor values. So first of all, we need to know that to calculate the inductance, we need the output voltage, we need the input voltage, for sure the switching frequency, and the maximum ripple current. So output and input voltage is something which is given by my application, and the switching frequency is given by my IC. So everything I know, what is about the maximum ripple current? We can see it how to make an assumption on the next page. So this is the easiest way to calculate. And as I told you before, we know the input voltage, the output voltage, and also the diode voltage is clear to me. But what is below here? The RCR. So this is my ripple. And to calculate this ripple current, or the ripple for which is multiplied by the current here, I need to make an assumption. So, and the assumption is usually something like 33%, or we can also calculate this. DI is ripple voltage divided by ESR, and the ESR is also given from my component, from the capacitor. So I can calculate this, and then I can see the ripple is 33%. So this is also an assumption which is done very often to do a start value like 33%. And then later we will see that this will change, because in the next step, when I use all these values and calculate my inductance value, I get 40.44 microhenry. for sure, there's no 40.44 microhenry inductor available. So by changing the value, I change also the ripple current. But now, which inductance should I choose? 33, 47, or 39? Well, you can get a sample box from us and make your own tests, but as first you need to do an assumption. Let's assume something. Let's say your idea is, or the idea of someone who is calculating this one is, oh, I don't want to take the 47 microhenry because the maximum current is lower and the RDC is too big or the item is too big. The 39 microhenry is a special item. It is not available from all manufacturers. So let's try the 33 microhenry because we have this on our warehouse. So this is the first step someone might think. Now, let's assume we have 10% inductance loss due to saturation or tolerance. Saturation is something I will go much deeper in a few slides. But in this case, our remaining inductance is just 30 microhenry, which is 10% loss of 33 microhenry. And that means our inductance is 25% lower than we initially calculated. And what does that mean? If we look here and we know that the input voltage and the output voltage and also the current and frequency are constant, the only thing that changes is my ripple current. And if I have a 25% lower inductance, that means I have 33% higher ripple current. And this is not good. So we should always prefer a higher inductance value. So now, for those of you who might think this makes no sense, 25% and 33% higher ripple current, I can give you the mathematic equation behind this. So 25% lower inductance is remaining 75%. This is 3/4, and this will finally be 4/3 higher ripple current. And this is 33% higher ripple current. Just to give you a short. If you still don't believe me, you can call me later. So now let's read the data sheet. And this is the data sheet of our MPX series. And this is just a screenshot of one value, which is 47 microhenry, because I just said 47 microhenry is better than using 33 microhenry. And what I can see is, I see a tolerance, that's clear, DC resistance, typical and maximum. And then I can see 3 rated current values, which are given. And I can see what all of these mean. We have the first one is 40K rise at current. Okay, we can see 20% and 30% inductance drop here. So we give 3 different values. To explain that, the IRMS is when the temperature rise of the inductor is 40K above the ambient temperature. This is the self-heating. Here you can see a graph. And actually the dark blue curve, this shows me the temperature rise. So the more current I put on my component, the higher it gets. And this means we define one point, which is here, the temperature rise of 40K or 40 degrees Celsius. And this is, in this case, something around 3.4 amps. And this is my temperature rise. Please keep in mind, this is just one point on the curve. This is no limit yet. The saturation current is when the inductance drop by 20% or 30%. So there's one point where we measure and we can see at this current value, and in this case it's 3.7 amps, we have an inductance drop of 20%. And the 30% drop would be somewhere around here, 4 point something amps. Also, this is just a point on the graph. It's no limitation, it has nothing to mean for now. And I want to explain you now more detailed how to interpret it. So temperature rise and saturation currents are no standard values, and they can vary from different manufacturers and also from each manufacturer. So these are 2 older components we have, and you can see sometimes even we are showing 30% and 20%. And I can clearly show you the same picture from competitors, because it's not a standard. You have seen in the previous page that for our new MPX series, we give both values, 20% and 30%, to make it more visible. And also in the data sheet, you can find the graph. So that makes it very simple for you to see the right values. But actually, the current value is just 1 point on the graph. To understand the IRMS, you must know that the ambient temperature plus the temperature rise must be lower than the maximum operating temperature of the inductor. I give you an example. Let's assume your ambient temperature in your application is 85 degrees. Well, if we take now the MPX Metcom power inductor from KEMET, it has 155 degrees as maximum operating temperature. And this means the maximum allowable temperature rise of the inductor is 70 degrees. And going back to the picture we saw before, yes, for sure, there's one point where you have a self-heating of 40 K, but your maximum temperature is much higher. And you can be okay up to 70 degrees self-heating. And this is much higher current. In this case, it's something around 4.1 amps. This is something which needs to be considered because the 40K is just 1 point on the graph and could not be the maximum. It could be the maximum depending on your application. And now the saturation current. Again, the saturation current describes 1 point on the graph, inductance over current. In this example, I have 3 different inductors. The dark blue is our Metcom 47 microhenry coil, which has a very smooth saturation. It's nearly constant. Then we have the light blue, which is also a Metcom inductor, but only with 33 microhenry. And then I've put here an old component, a standard component with 47 microhenry. And you can see the main difference. Depending on which current you are using, it has more influence using the yellow standard item or to use the Metcom technology. So ideally, the current and ripple must be checked for each inductor. And the question is, what is the output current? Is it 0.5 amps? Is it 1.5 amps? Or maybe it's 2 amps. So if it's a very low current, there's not much difference here at this point. But if your current is higher, let's say in this point it's 1.5 amps, you can see there's a high difference between the standard item, the yellow curve, and the Metcom item, the dark blue. And even if you are looking at a high current like 2 amps or maybe 2.5 amps, it would even be better to use a Metcom 33 microhenry coil instead of a standard 47 microhenry coil. And why is this so bad? I can show you in the next picture. I will show you now the influence of the ripple. And let's say we take the example I just had before with 1.5 amps. 1.5 amps, and then we have a ripple current. In our example before, I said it's 33%. But if now the ripple current changes by 33%, then also my inductance value changes from somewhere between 39 microhenry up to 41 microhenry. So I'm far below my initially calculated 40 microhenry, and I have a huge change of inductance. This is for the standard item. If I now choose the Metcom inductor with soft saturation or smooth saturation, and I do the same at 1.5 amps, I still have my 33% ripple, but the change of inductance is much lower here. And this is the reason why I always have a better result if I take a smooth saturation or soft saturation, however it is called. And this big inductance drop is always bad. And this is for you the first point how to understand if an inductor is good or bad. You need to know where's your output current and you need to know how is your ripple current. And then you can see if it's a problem like in the picture before, or if it's like here, no issue. Even if your ripple current is 40% or 50%, then you have still not that big loss of inductance. So as a summary, I can say the inductance drop must still work with a ripple current. A decrease of inductance is equivalent to an increase of the ripple current. But the ripple current should be as low as possible, because when my inductor goes in saturation, I will have negative impacts on my efficiency finally. Now we know where to look at, but let's compare the data sheets. And by comparing data sheets, so our MPX series with competitor items, I found something. Well, this is one competitor item. It's also 47 microhenry. And the first thing I can see is, well, the saturation current is a little bit different. Also, this competitor is giving 20% and 30% and 40K. You must read always what is written below, like here, if it's the same values or if it's different. But then there's one hidden secret. I don't know if you have seen it. We also give here an IRMS of 3.3 amps. But the maximum temperature is 125. So this means, sorry for this, my maximum, I have maximum 3.3 amps at 85 degrees. And this is the massive difference between this item and our item, which goes up to 155 degrees. So sometimes it's not only the value we are reading here or the 40K we are reading here, but also the operating temperature range. And here we have another competitor. And also this competitor is quite interesting because the first comparison I can make, and this is also again a 47 microhenry item, I can see, well, the saturation current at 20% drop is higher than ours. Well, at first I would say, nice item, let's take this one. But then when you read further, you can see, oh my God, 2.2 amps at 40K self-heating, which is much less than our item. And again, we have the same situation that we have the 2.2 amps at a temperature rise of 40K. So my maximum allowable temperature is 85 degrees. So if you look at the 4.5 amps, yes, that's nice product, but I can never use the 4.5 item, 4.5 amps, because this means I need to cool it down to minus something degrees, and this will never happen. And this is something which need to be also considered. These values are really constant and nearby each other. So this makes it possible to use this item maybe at 5 amps, depending on which temperature you have. But the main limitation of those two competitors is the maximum operating temperature up to 125 degrees. And therefore, I can use my KEMET component with maximum 4.5 amps at 115 degrees, or much higher than 4.5 amps at 85 degrees. And you can read this in the data sheet. So the first view might not give that much difference, but we can see here now that always read what is written at the end of the data sheet, and especially for the operating temperature, because this is your limitation and this is finally your maximum temperature or your maximum current you can use this item. So let's make a short summary for saturation and IRMS. Saturation current and IRMS are independent values and need to be considered separately. And each application must be considered concerning the ambient temperature and the maximum inductor temperature for IRMS, the maximum ripple current of the DC-DC converter for the saturation current. And please keep in mind, ISAT and IRMS are no limitation. There are no maximum values. The only maximum value we are giving, or one of the maximum values, is the maximum operating temperature. And this is the limitation. And therefore, you need a low RDC. This is important for less DC losses and high IRMS. Well, we have seen just in the picture before that we have a very high RMS with our MPX series. The operating temperature really indicates your maximum current. And we have seen in the picture before also, our KEMET MPX series goes up to 155 degrees. We need this smooth or soft saturation for high ripple currents, and this is given by our KEMET METCOM technology. And you should choose a molded design for low EMI. This is something I will show in one of the next slides. And for sure, you need an optimized material for higher switching frequency to increase your frequency maybe up to 1, 2, or 3 megahertz. Now, at the end, just a few slides for our metal composite power inductor. Just for you to know, some of them are calling this iron powder or metal powder. In fact, it's all the same. From inside, it looks like this. We have many, many small balls, and this is metal powder, and they are pressed together. But each of the ball has an insulating coating and is not contacting each other. And we are doing this because this is our air gap. This is what we have when you remember the second picture in my presentation with the effective length. This is my air gap, and I have many, many millions of air gaps in my material. But the main advantage with this technology, and here we can see what I meant with assembled inductor, the molded inductor is totally pressed. The assembled inductor has here an air gap. Yes, it is filled with something, with glue or something, but out of this air gap here, you can have a magnetic field which goes outside of the component at the top. And this magnetic field can cause EMC issues. And the molded design we are using with our KEMET MPX series has the magnetic field fully inside the component and less magnetic field outside of the component. And also here, when you look at the difference between the metal molded type and the assembled type, you can also see that there's a big drop at one point for the saturation current. And therefore, we just seen a few slides ago that the soft or smooth saturation is much, much better, only if you have just a few amps. But usually you are using your component at nearly the edge of the maximum current. Therefore, the metal molded case is better. And this is now our series, our latest series, which we have also seen on our presentation last Monday, our MPX standard series, or MPXV for vehicle, which is our automotive power inductor series. And this is how it looks like. You might have seen this picture before. You can see here now the winding inside, and then on this side, we have the metal termination. We have a metal composite shielded inductor, and also a very high inductance range from 100 nanohenry up to 100 microhenry. The rated current range goes up to 90 amps, and we have 15 different case sizes from 5 by 5 millimeters up to 22 by 20. A bigger case size would be not possible in SMD, it would fall off the board. And finally, and this is the most important thing, and I hope you have seen it and understood it, that the operating temperature up to 155 degrees is the most important thing we can offer, and this gives us a very much higher maximum current of the component. And with this question and this short information about our MPX series, I'm at the end of my presentation.
I would like to thank Alex for the really nice and detailed presentation today. If you have any more questions, please do not hesitate to contact Alex, myself directly. And thank you very much for attending this webinar, and have a great week, everyone. Thank you, Alex.
And thank you also from my side, and hope to see you soon again.